Welcome to the next session of subject engineering maths. Now in this session we start with chapter number 4, that is complex variables. The weightage of complex variables is approximately 2 marks in the competitive examinations like GATE, even IES, Indian Engineering Services, right? So particularly this topic is not included for computer science students. It is for all students except for computer science. Okay. Now let us see what we discuss in case of complex variables. Let me give you some overview. Suppose when you take variables, we have in the mathematics world we have exactly two types of variables. One is a real variable. One is a real variable. And another one is a complex variable. Real variables and complex variable. Generally, real variables we can denote them as x or y, but in case of complex variables they will be denoted as z. Basically, this z is nothing but combination of two variables internally, that is x and y. Now, what is this I? Here I is nothing but a number whose square is -1. But here I am saying that I is a number whose square is -1. There is no real number whose square is -1. When you square any real number, the value is always greater than or equal to 0. Square of, suppose if x is a real number, then x square is always greater than or equal to 0. That is, this is a non-negative expression. So therefore, in this case, I am writing I square equal to -1. That means this is not a real number. If I assume that there is some number whose square is -1, then such numbers are called imaginary numbers. So here we were in two worlds. One is real world and second one is imaginary world. So that means if I assume that there is some variable, there is some number, instead of using variable, I use number. If there is some number whose square is -1, then such numbers are referred to complex variables. They are imaginary numbers. Basically, complex numbers are our imaginary numbers. We were assuming, right? Now, if I assume that there is some number whose square is -1, I have many advantages. The basic advantage of discussing complex variables is, one is contour integration. Contour integration. Let us see what does contour integration. In case of real numbers, generally in case of integrals we use the symbol like this. Integral a to b f of x dx. That means we were discussing the area bounded by f of x between the lines x equal to a and x equal to b. So what it defines, integral a to b f of x dx defines exactly area bounded by f of x between the lines x equal to a and x equal to b. So if the boundaries are two straight lines, so finding real integration is simple for me. Of course, f of x must be continuous in closed interval a comma b. But in case of, suppose if I want to find the area bounded by f of x over a circle, over rectangle, then it may not be simple for me. Therefore, in case of complex variables, generally the integrals will be like this. Integral f of z dz over c. Basically, this is a simple closed curve in the complex plane. Of course, when you want to discuss this f of x must be continuous in closed interval a comma b. Basically, this is nothing but area bounded by f of x between the lines x equal to a and x equal to b. But suppose if the boundaries are not straight lines, if the boundary of a curve is a circle or something else, then we can't go for real integrals. Therefore, in order to get the recovery from this, we have complex variables. So in this case, generally z is a complex variable, and here we integrate f of z over some contour. Contour means a simple closed curve in the complex plane. So to get these values, we have some complex variables z. So at the end of complex variables, we go for contour integration. Our ultimate target in case of complex variables is finding contour integration, that is integral f of z dz over some contour c. So to achieve this, we have many basics in the complex variables. So hope you understand. So what is the motto to discuss complex variables? We have a single task, that is Finding contour integrals. That is integral f of z dz over c. This is a complex valued function because z is a complex variable and c is a contour. Contour means a simple closed curve in the complex plane. Okay. Now let us start with basics. In this session, we go for basics, definitions of complex number, argument of a number, modulus of a complex number, complex conjugate followed by circle, properties, analytic function, differentiable functions, etc. etc. Okay. Now let us start with definition of complex number. Suppose I have a number of the form a plus ib where I square equal to minus 1. Then such numbers are complex numbers. In this case, a and b are called as real numbers. That we denote it as R. I have a number a plus ib where a and b are real numbers and I square is equal to minus 1. Such numbers are called complex number. Generally, we denote them as a variable z. So frequently we use the variable z to represent a complex number. So how to define this? A number of the form z equal to a plus ib where a and b are real numbers and I square equal to minus 1 is called a complex number. Let us take an example. Suppose I have z equal to 2 plus 3i. This is one complex number. Suppose I have z equal to 3i. This is another complex number. And for example, z equal to 2. This is another complex number. Here this 2 I can write it as 2 plus i0. This 3i I can write it as 0 plus 3i. Now this is a real number, it's a real number. 0 is a real number, 3 is a real number. 2 is real number, 0 is real number. So in that case, all the three examples will be called as complex numbers. Now, if I have a complex number z equal to a plus ib, this a is called real part of z. So this a is called real part of z. And this b is called imaginary part of z. This b is called imaginary part of z. Generally, we denote them like this: re of z, real part of a complex number z, that is a. Imaginary part, we can write it as im of z, that we can write it as b. Okay. So this a is called real part of z and b is called imaginary part of z. First, write the definition. Complex number. Complex number. A number of the form z equal to a plus ib. A number of the form z equal to a plus ib is called a complex number. A number of the form z equal to a plus ib is called a complex number where a and b are real numbers, and I square equal to minus 1. Where a and b are real numbers and I square equal to minus 1. Examples. Note down these three examples. First one is z equal to 2 plus 3i. Second example, z equal to 3i. You write it as 0 plus 3i. Third example, z equal to 2. Write it as 2 plus i0. Note. Note. In the complex number z equal to a plus ib. In the complex number z equal to a plus ib, comma a is called real part of z and b is called imaginary part of z. In the complex number z equal to a plus ib, comma a is called real part of z and b is called imaginary part of z. They are denoted by re of z and im of z. They are denoted by RE of Z and IM of Z. Therefore, RE of Z equal to A, comma, IM of Z equal to B. RE of Z equal to A and IM of Z equal to B. Now let me make some comments on real and imaginary parts. So I have a complex number Z equal to A plus IB. What is my real part? RE of Z equal to A. What is imaginary part? IM of Z equal to B. IM of Z equal to B. Now in this case, this is called real part and this is called imaginary part. Now let us see. In this case, I have a non-zero real part as well as a non-zero imaginary part. But when you look at this, here real part is 0. When the real part is 0, such complex numbers are called purely imaginary complex numbers. We have generally complex number contains two types of fields. One is a real part, second one is imaginary part. But in case of example 2, I don't have real part. That means I don't have means it is 0. But imaginary part is non-zero. Therefore, if I have a complex number Z equal to A plus IB, if A equal to 0 and B is not equal to 0, then such numbers are called purely imaginary numbers. They are called purely imaginary numbers. This is one case. Suppose case 2. Suppose A is non-zero and B equal to 0. They are called as purely real numbers. They will be called as purely real numbers. So when you go through examples 2 and examples 3, you can understand very easily. Here real part is 0, but imaginary part is non-zero. So therefore this is a purely imaginary number. Now in this case real part is non-zero, but imaginary part B is 0. Therefore they are purely real numbers. Okay. Now when we gone through chapter 1, that is linear algebra, we have gone through eigenvalues of real skew symmetric matrix. They are either 0 or purely imaginary. Hope you understand. So therefore complex values play very important role even in case of eigenvalues of a square matrix. Okay. Sometimes when you take a real symmetric matrix, eigenvalues are real. When you take a real skew symmetric matrix, eigenvalues will be either 0 or purely imaginary. Purely imaginary. Thus, in this case, you can understand what is purely imaginary, what is purely real numbers. Note these points. Note, if A equal to 0 and B not equal to 0, if A equal to 0 and B not equal to 0, then Z is called a purely imaginary number. If A equal to 0 and B not equal to 0, then Z is called a purely imaginary number. Second note, if A not equal to 0 and B equal to 0, then Z is called a purely real number. Then Z is called a purely real number. Next, second definition, complex conjugate. Suppose I have a complex number Z equal to A plus IB. Now its complex conjugate is denoted by either Z bar or Z star. So this is the symbol to find the complex conjugate of Z, or you can use Z bar or Z star, and this is again a complex number which is equivalent to A minus IB. This is my complex number Z equal to A plus IB. Its complex conjugate is denoted by either Z bar or Z star, which is again a complex number that is equivalent to A minus IB. That means what we were doing is I is replaced by minus I. I is replaced by minus I. Suppose when you treat this point as a 2D point A comma B, so two-dimensional plane, so I am writing R square. A comma B belong to R square. This is two-dimensional point, we can write it as A plus IB. Now what is the corresponding two-dimensional point in this case? this is A comma minus B. Therefore, when you look at this, this is x-axis and this is y-axis. For example, when you consider this point, for example, 1 comma 2. So what does it mean? This is referred to 1 plus 2i, a complex number. Now its complex conjugate is 1 minus 2. This is nothing but actually 1 minus 2i. Now basically this will be located at this point and this will be located at this point. For example, this is P and this is Q. Now you can see basically this is nothing but reflection of 1 comma 2 about x-axis. See, suppose I'm standing at this position. Suppose if I face a mirror at this moment, suppose the distance between mirror and myself is, for example, 2 units. So how my reflection will be? It will be again backside of this mirror, but distance will be same. So suppose if I keep mirror at this moment, suppose if the distance between my face and mirror is, for example, 1 unit, then my face will be available on the backside of that mirror. Again, it maintains the same distance. So that means that image will be called as a mirror reflection of my image. Yes or no? The same case here, which is acting as mirror, x-axis. Suppose you keep mirror at this moment. So therefore here the distance will be something. So the distance will be again same. So therefore basically this is nothing but reflection of 1 comma 2 about x-axis. In this case, what is my mirror? Mirror is x-axis. So therefore when you take a complex number z equal to a plus ib, its conjugate is denoted by either z bar or z star, and that is nothing but a minus ib. If I treat this as a 2D point a comma b, then this can be again equivalent to a minus b. Now if I go for geometrical representation, suppose I have a complex number 1 comma 2, point-wise notation. That is, this is 1 plus 2i. This is the real part and this is imaginary part. Then its equivalent reflection point is 1 comma minus 2. This is 1 minus 2i. Therefore, this point is nothing but reflection of 1 comma 2 about x-axis. Hope you understand this. Now, in this case, let us see. Suppose I have one example. Suppose I have a complex number z equal to 2 plus 3i. Now, in this case, what is my z star? This is 2 minus 3i. Now, I go for general now. So, here z equal to a plus ib. And here z star equal to a minus ib. Now let us add these two. Z plus z star equal to ib minus ib gets cancelled. I will get 2a. So this implies this a is nothing but z plus z star divided by 2. Now what is this a? This is real part of z. Therefore the conclusion is real part of z is z plus z star divided by 2. This is one conclusion. Real part of z is z plus z star whole divided by 2. Now, if I find the difference of these two, what I get is, just go through the difference, z minus z star. So, real part will be cancelled. I will get 2ib. Therefore, in this case, b equal to z minus z star divided by 2i. But what is this b? This b is nothing but imaginary part of z. Therefore, in this case, imaginary part of z is z minus z star divided by 2i. So this is one useful result. So both are very important points. We have expressed real part of a complex number in terms of complex number and its conjugate. Similarly, we have expressed the imaginary part of a complex number z in terms of a complex number and its complex conjugate. Okay. So note these points. First, write the definition. Let z equal to a plus ib. Let z equal to a plus ib be any complex number. Let z equal to a plus ib be any complex number. So stop. The complex conjugate of z is denoted and defined as z bar or z star equal to a minus ib. Z bar or z star equal to a minus ib. You can have this coordinate system, x-axis and y-axis, followed by these two important points. Okay. Now we make few comments. First note, the complex number z equal to a plus ib. The complex number z equal to a plus ib is equivalent to a 2D point a comma b. The complex number z equal to a plus ib is equivalent to a 2D point a comma b. Is equivalent to 2D point a comma b. Next note. If a plus ib is a complex number, then its complex conjugate is reflection of the point a comma b. Then its complex conjugate is the reflection of the point a comma b about x-axis. The reflection of the point a comma b about x-axis. Let's consider properties of complex conjugate. Properties of complex conjugate. Now I have two complex numbers z1 comma z2. So z1 comma z2 belong to C. This is a complex plane, set of complex numbers. Now when you add these two, z1 plus z2, I will get a new complex number. These are my two complex numbers, z1 and z2. Add them, I will get new more complex number. So for this, apply conjugate. This becomes z1 bar plus z2 whole bar. So if I apply minus, I get minus. So therefore, this is called linear property. Now replace plus or minus by dot. z1 into z2. Multiply two complex numbers, I will get new complex number. Apply conjugate for this, you will get z1 bar times z2 bar. Even this is also called as linear property. Now when you replace dot by division, z1 by z2, so ratio of two complex numbers, I will get new complex number, apply conjugate, and this becomes z1 bar divided by z2 whole bar. Even this is also nothing but a linear property. Therefore, in case of complex conjugate, plus follows linear property, minus follows linear property, dot follows linear property, even division follows linear property. So note all these properties. Suppose we have a complex number z equal to a plus ib. Now its modulus is denoted by this mod z equal to, this is given by the expression square root of a square plus b square. This is my complex number z equal to a plus ib. Its modulus is denoted by this mod z, and that is defined by the expression square root of a square plus b square. Basically it is in the form square root of a minus 0 whole square plus b minus 0 whole square. Now this is nothing but distance of the point a comma b from origin. Distance of the point a comma b from origin. x1 y1, for example x2 y2. So this is x1 y1 and this is x2 y2. What is the distance between x1 y1 and x2 y2? The expression given by like this: square root of x2 minus x1 whole square plus y2 minus y1 whole square. Therefore, when you take a complex number like this, then its complex conjugate is denoted, its modulus is denoted by this, and which is defined as square root of a square plus b square. Okay. So previous one is complex conjugate, that is z bar a minus ib. Now this is mod z. it is purely a real number. So when you discuss modulus of a complex number, the result is real number. When you apply complex conjugate for a complex number, the result is again a complex number. Try to understand the difference. Okay. Now therefore, let us take an example. Suppose if I take z equal to 2 plus 3i. Now its modulus is denoted by square root of 2 square plus 3 square. So this is given by root 13. If I take its complex conjugate z bar, this is 2 minus 3i. Now apply the modulus of this, modulus of z bar. So this is square root of 2 square plus minus 3 whole square. This is again root 13. So this is my complex number and this is my conjugate. So both complex number and its complex conjugate will have same modulus. Therefore, the conclusion we have is modulus of z equal to modulus of z bar. This is one very useful point. Okay, modulus of z is same as modulus of z bar. So write the definition. Let z equal to a plus ib. Let z equal to a plus ib be any complex number. Let z equal to a plus ib be any complex number. The modulus of z is denoted and defined as mod z equal to square root of a square plus b square. Mod z equal to square root of a square plus b square. So that is equal to square root of a minus 0 whole square plus b minus 0 whole square. This is equal to distance of a comma b, point-wise notation. Distance of a comma b from 0, 0. Distance of a comma b from 0, 0. Now this is the example. Write this and comment like this: mod z equal to modulus of z bar. Now we discuss properties of modulus. Suppose I have two complex numbers z1 comma z2. Then add these two complex numbers z1 and z2. I will get new complex number. This is my complex number. This is complex number. Add these two. I will get new complex number. Apply modulus. So can you guess the relation between modulus of z1 plus z2 in terms of mod z1 plus mod z2? So I need to establish what is the relation, whether it is equal or less than or greater than. So modulus of z1 plus z2 and mod z1 plus mod z2. Suppose this is x and this is y. So suppose if this entire expression is x and this entire expression is y. So what is the relation? It is a real number because we are applying modulus. We are applying modulus, it is a real number. When you take two real numbers x and y, I can have only one relation. The relation can be either x less than y or x greater than y or x equal to y. So therefore let us see what will be the relation between x and y in this case. What is my x? Modulus of z1 plus z2. What is y? Mod z1 plus mod z2. Let us discuss by taking an example. Suppose z1 equal to 2, z2 equal to 3. Now in this case, modulus of z1 plus z2, this is nothing but mod 5. This is equivalent to 5. This mod 5 I can write it as mod 2 plus mod 3. This 5 I can write it as modulus of 2 plus mod 3. This mod 2 I can write it as modulus of z1 plus modulus of z2. Therefore, if Z1 and Z2 are purely real numbers, then modulus of Z1 plus Z2 equal to mod Z1 plus Z2. Of course, they are positive numbers. But next case, I will take one positive and another is negative. Suppose if I take this, Z1 equal to 2. For example, Z2 equal to minus 3. Now, what is modulus of Z1 plus Z2? Modulus of 2 minus 3, this is modulus of minus 1, it is 1. When you go for individual modulus, modulus of Z1 plus mod Z2, this is equal to modulus of 2 plus modulus of minus 3, this is 5. Now here this is 1, this is 5, so 1 is less than 5. So therefore, from this example as well as this example, the relation between these two expressions is, in some cases it is less than, in some cases it is equal. So in this case, it is less than, but in this case it is plus. So therefore, the conclusion we have is modulus of Z1 plus Z2 is less than or equal to modulus of Z1 plus modulus of Z2. And this property we can call it as a triangle inequality. This property we can be called as a triangle inequality. Suppose in place of plus, if dot is written, multiplication, modulus of Z1 dot Z2. So this is nothing but mod Z1 times mod Z2. So this is called linear property. Now replace dot by division. So therefore this is a modulus of Z1 by Z2. This we can write it as mod Z1 divided by modulus of Z2. Again, this will be called as linear property. So therefore, first one is triangle inequality, but when you take dot and division, they follow linear properties. Note these points. Next definition, argument. Suppose we have a complex number Z equal to A plus IB. Now the argument of this complex variable Z is denoted by ARZ of Z. This is my complex variable. Its argument is denoted by ARZ of Z. Basically, argument represents some angle theta, and this is given by the expression tan inverse of B by A. So whenever this is my complex number, its argument is denoted by this ARZ of Z, which represents some angle theta, and that is given by tan inverse of B by A. Tan inverse of B by A. Suppose if I take complex number like this. Example. Suppose Z equal to, for example, 1 plus I. Now let us see its argument value. Here argument of Z is theta equal to tan inverse of B divided by A. Here A value is 1, B value is 1. So therefore this, in this case, this is the tan inverse of 1, and this is given by pi by 4, that is 45 degrees. Now let me tell you two important results based on arguments of product of two complex numbers and argument of ratio of two complex numbers. The two results we have is, first one is argument of Z1 dot Z2, and this is given by argument of Z1 plus argument of Z2. That means this dot becomes addition. Similarly, when you try to find argument of Z1 by Z2, so argument of ratio of two complex numbers, this division becomes subtraction. So argument of Z1 by Z2 equal to argument of Z1 minus argument of Z2. They resemble these two formulae. When you look at logarithmic function, log AB, this is same as log A plus log B. That means when you apply log for dot, this dot becomes plus. Similarly, when you apply log for ratio, it becomes minus. These are very basic results. Okay, we have complete awareness about this. Log AB equal to log A plus log B. Log A by B equal to log A minus log B. So exactly these two results exactly resemble these two results. These are real numbers, these are complex numbers. So therefore, argument function just like behaving as a logarithmic function. Okay, note these points. Let Z equal to A plus IB. Let Z equal to A plus IB be any complex number. Let Z equal to A plus IB be any complex number. First of the argument of Z is denoted and defined as ARZ of Z equal to theta equal to tan inverse of B by A. ARZ of Z equal to theta equal to tan inverse of B by A. You write this example and followed by these 2 points. Next definition, fixed point. Suppose we have a complex valued function f of z. What is this? This f of z is a complex valued function. So that means when z is a complex number, f of z becomes again a complex number. Such functions are called complex valued functions. Suppose z0 is some complex number. We say that z0 is a fixed point of this if f of z0 equal to z0. If f of z0 equal to z0, then z0 is called fixed point of f of z. That means image of z0 with respect to f is itself. Let me tell you one simple example. Suppose if I take general examples at lower standards, suppose if I use this example 1, 2, 3, for example 1, 2, 3, 4. Suppose this is set A and this is set B. If I go for mapping like this, assume that 1 is mapped to 2, 2 is mapped to 1, 3 is mapped to 3. Now therefore this is a function. Every element of A is mapped to exactly one element of B. Now it's a function. Now what is image of 1? It is 2. What is image of 2? 1. But image of 3 is 3. What does it mean is f of 3 equal to 3. Therefore 3 is a fixed point of this function. 3 is a fixed point of this function. This is example 1. If I take example 2, that is complex variables. Suppose f of z equal to, for example, this I can write it as, for example, z plus 1 by z minus 1. Now I want fixed points of this complex valued function. Suppose if z is a fixed point, then f of z must be equal to z. So what is f of z? Z plus 1 by z minus 1 equal to z. So this implies z plus 1 equal to z square minus z. So this implies z square minus 2z minus 1 equal to 0. Now here this is a quadratic equation. Coefficient of z square is a, coefficient of z is minus 2 and c value is minus 1. Therefore what are its roots? So its roots are z equal to minus b plus or minus square root of b square minus 4ac divided by 2a. So z equal to, here b is minus 2. So therefore this is plus 2 square root of b square means 4 minus 4 into a into c. So you will get plus 4 divided by 2a. So therefore z equal to 2 plus or minus root 8 by 2. So this is 2 plus or minus this root 8, we can write it as 2 root 2 divided by 2. So one fixed point I can write it as 1 plus square root of 2. Second fixed point I can write it as z2, this is 1 minus square root of 2. Therefore in this case my fixed points are 1 plus square root of 2 and second point is 1 minus square root of 2. Now it is a complex valued function. But when you take a real function, just by going through the mapping, you can easily say that 3 is a fixed point of this function. Okay, note this point. Let f of z be any complex valued function. Let f of z be any complex valued function. And z0 be any complex number. Let f of z be any complex valued function and z0 be any complex number. We say that z0 is a fixed point of f of z. We say that z0 is a fixed point of f of z if f of z0 equal to z0. If f of z0 equal to z0, that is image of z0 is itself with respect to f. that is image of Z0 is itself with respect to f. So here you write it as example 1. In this case 3 is the only fixed point. But when you look at this Z plus 1 by Z minus 1, when I apply the definition, if I assume Z is a fixed point, f of Z equal to Z. So from this, if I derive, I will get a second degree equation. I will get two roots. They are 1 plus root 2 and 1 minus root 2. So therefore this Z1 and Z2 are nothing but fixed points of this complex valued function. Okay. Write these examples.